Hello, everybody. It's good to be back here at DPC. I last spoke here in 2017. That was in the before times. So HTTP is a critical part of our lives as web developers. So when it changes, we need to know what's different, and that's why I'm here today. To save a lot of talking, you might hear me refer to H2 and H3, because HTTP, having to say that a lot of times is just a bit of a pain. So how many of you are already using HTTP 3? 2, 3, maybe. Okay, it's probably more than that. You just don't know. We'll see. So who am I? Well, I am a skier, mainly. I've skied 58 days this season. I write songs about open source and web development, so go listen to them. I was originally British, but I escaped after Brexit, and I'm now French. If you've encountered my stuff, it's probably as I'm the maintainer of PHP Mailer. But I also work as a Laravel developer and sysadmin, and I do lots of work for this company called Radically Open Security, who's a pen test agency based here in Amsterdam, though I live in France. So as part of these roles, I've worked configuring servers, and I heard about this HTTP 3 thing, and I thought I'd give it a go, and found that it was actually quite straightforward, but I did have to look stuff up to find out how to do it, so I thought, this will make a good conference talk, so I proposed that. And then I did that at a couple of conferences, and then one of the conference organizers said, hey, can you turn this into a magazine article? So I wrote a 4,000-word article in 2 hours. I was quite impressed with myself. And then I thought, well, that was so easy, I should really expand this, so I wrote a book about HTTP 3 and self-published that on LeanPub. And of that, I've now been approached by A-Press, who want me to write a bigger book. So this conference talk has got really out of hand. Anyway, let's jump in and say, well, how did we get to this point? Way back in the mist of time, in 1991, Tim Berners-Lee came up with this thing, which is kind of loosely termed HTTP 0.9. There wasn't an RFC. It's very basic. It only supported GET, and it only supported HTML. Those were dark times. What happened then is browsers came along, like Mosaic and Netscape, and they started inventing really cool, useful things like Marquee and Blink. But they also added post and other verbs, and also MIME. So we could do things like we could post forms, we could have images. It was all much prettier at that point. HTTP 1.1 came along just a year later, and that added keep alive and pipelining, which made things much more efficient. It also added the host header, so that gave birth to the entire industry of virtual hosting. And it had continuous updates all the time up until 2014. Finally, in 2015, we got HTTP 2, which added a binary protocol and stream multiplexing. And then finally, HTTP 3, 2 and a bit years ago in 2022. So looking back, what did HTTP 2 change? Because there were a whole load of conference talks about that. Well, the number one thing really is that it switched to using a binary protocol. And this was pretty much entirely transparent to your everyday use of it. You probably didn't even know this was happening. But really, it's a more compact representation of the stuff sent over the wire, and it also allowed us to do header compression, because headers these days can get pretty big. If you're using things like JWTs, it really helps to be able to compress headers like that, which we couldn't do before. Binary protocol is easier to write parsers for as well. It's slightly more predictable. So you have, say something like 200 OK as a response in HTTP 1.1. That would be represented as 6 ASCII characters. So you've got a 2 and a 0 and a 0 and a space and an O and a K. So you've got 6 bytes there. That's really quite a bit. Whereas in a binary protocol, we could just express that value as just as an integer. It also added multiplexing. Now, prior to HTTP 2, if you wanted to send multiple resources at the same time, you had to open multiple TCP connections, and each one of them had to do its own TLS handshake and so on. It was quite an overhead to set that up. But in HTTP 2, we can actually send multiple things over the same TCP connection simultaneously. But there are some problems with that, we'll see. It also added server push. When your browser requests an HTML page, that HTML page is probably going to refer to other sub-resources like images, styles, scripts, and so on. And the server could take a gamble that the next thing you were going to do was ask for those things. So in addition to the HTML response, it would also bundle further resources tacked onto it before you'd even asked for it. And the idea then is that the browser would receive those and put them in its cache, and then when your browser parses the HTML document, finds a reference to it, and finds it's already got it in its cache. But that really didn't get used very much because it actually tended to just generate lots of unnecessary traffic. It was also TLS only. Strictly speaking, the HTTP2 spec can be used over unencrypted connections, but in practice, there are no implementations that actually support it. So what are the problems with HTTP2 that we need to fix? Well, the number one thing is this thing called head-of-line blocking. Now, this is all about stalled transfers holding up other transfers that are queued up behind it, and I'll explain more about that. There's also a problem with network switching. Every time you switch between, say, your home Wi-Fi and a mobile connection, it has to re-establish all the connections. And this can make things very slow, because you can imagine on a phone, you might have hundreds or even thousands of simultaneous connections that need to be recreated. There are some problems that HTTP2 is built on top of TCP, which is part of the operating system layer, which you can't really do anything to alter. So if it doesn't work quite the way you want it to, well, tough, you're just going to have to live with it. And it would be really nice to be able to change that. So what are QUIC and HTTP3, and why do we need them? Well, as I said, we can't change the way that TCP works without replacing pretty much every device in the world or updating every operating system. And that's a big problem. There's a huge amount of inertia. So we really can't change TCP very much. So Google designed QUIC in 2012 as a workaround for this. And fundamentally, it's a reimagining of TCP built on top of UDP. And I'll get into the difference between those in a bit. But fundamentally, it really combines the features of TLS and TCP into a single protocol with reduced overhead. And HTTP3 is really the same as HTTP2, but it's built on QUIC instead of TCP. The other thing that's a big difference is that it's implemented in userland and not in the operating system. So when you have something like a web browser or a server like Nginx, they have to have their own implementation of the QUIC layer. It's not provided by the operating system. So the disadvantage of that is it means that it's got to be implemented separately in every application. But the upside is that it's much more flexible and much more dynamic. Applications tend to get updated far more frequently than operating systems do. The other thing that's relatively unknown about it is that you're probably using it already. It's been around for a couple of years now, and Cloudflare, who were one of the early adopters of HTTP3, said that HTTP3 actually overtook 1.1 in the first year it was introduced in 2022. So if you're behind Cloudflare, I think they actually enable HTTP3 by default, so you may even be using it without even knowing. Let's have a look back at this TCP versus UDP thing. So TCP is part of your networking stack, and it has a bunch of features. It's complicated, but it provides a reliable transport on top of an unreliable IP layer. And that means that when we can transfer a resource, we can guarantee that it's going to turn up at the other end with all the pieces of it in the right order, reassembled in exactly the same configuration that it was when we sent it out from the server. But because of that, it can be a bit slow. Say there's a problem with one of these packets that's sent, it's going to hold everything up and wait for that to be retransmitted from the server. And then it can finally slot that missing packet into place and then get on with reconstructing the whole resource. This isn't necessarily what we always want to do. The user data brand protocol is also an IP-based protocol, but it's much, much smaller and simpler. And because of that, it's very fast. It's really simple to write parsers and so on for, but it doesn't provide a reliable service. Now, unreliable services are actually quite useful. It means that we don't have to worry about setting up connections. There's no handshake. You just start sending packets at a destination, and you don't care if they turn up at the other end. The packets can turn up in any order, and there's no particular guarantee that they're actually going to turn up at all. But this lossy nature is actually quite useful. Say, for example, you're in a video conference, and there's a packet is slightly corrupted, and it means that one of the pixels in the middle of the frame is slightly the wrong color. Big deal. Forget about it. We're just going to carry on. We really don't care about that data. Same goes for a lot of audio streaming. And also, it's used for DNS. So the way that DNS is typically set up on your average computer is you have multiple DNS servers configured, and it sends out a query packet with the name you're looking for. It just sends it out to all of those servers. It doesn't care if it actually turns up or gets to the other end at all. So long as one of those DNS servers responds, that's all you are interested in. You don't care which one it was or what happened to the other packets that never came back. So while UDP is faster than TCP, if we're going to re-implement the same kind of features that TCP provides, because ultimately we do still want to have reliable delivery of many resources. You don't want a JavaScript with a bunch of things missing in the middle of it. You need the whole thing to turn up intact. So while we're doing away with the way that TCP works, we need some of those features back again in QUIC on top of UDP. So ultimately, the speed difference isn't going to be that great because we're re-implementing the same things. But the difference is we get to choose exactly how we implement it, and we don't have to wait for the operating system to do it. So we end up that we're still better off than we were with plain TCP, and it's much easier to change. So how does it sit in our network stack? Well, down at the bottom, we've got IP4 and 6, exactly as before. And up at the top, we have HTTP that we know and love. In HTTP 1.1, we had a choice of running it with or without encryption, so we can have it with or without TLS, but it's still built on top of TCP. In HTTP 2, we lost that option to not use encryption, and it also has a minimum of TLS 1.2, but it's still built on top of TCP. HTTP 3 really changes things around quite a lot. I've drawn the UDP block here a bit smaller because the UDP is a simpler, more straightforward protocol, but it's missing lots of features, but those are then re-implemented in the QUIC layer on top of it. Now, QUIC is kind of, it's less like a direct replacement for TLS or TCP. It's really most like a sort of a big TLS extension, and we'll see why that's useful in a bit. And then there are very minor differences in how the actual HTTP layer functions, but ultimately it's all still HTTP as far as we're concerned as developers. So there are some differences in the network stack from an efficiency perspective. Now, this is a really common deployment here. This is HTTP 2 over TLS 1.2. So to make off a first HTTP request to the server, first of all, we have to do a TCP handshake to establish a connection. Then we have 2 round trips to establish a TLS session, and then finally we get to do our HTTP request. So that's 4 round trips before we get our first byte. That's quite bad. If we upgrade to TLS 1.3, it has some efficiency improvements, which mean that we get to lose one of those TLS round trips. But with QUIC and HTTP 3, we can lose yet another one because it combines the TLS and TCP layers into a single round trip. And then, so we establish a connection and we issue our HTTP request. So it's half the latency relative to TLS 1.2 with HTTP 2. But that's the initial connection. Once we've done that, we've then got some information about the connection which we don't need to repeat. We already know, for example, we know the IP address, so we don't have to do a DNS lookup. We can skip parts of the TLS connection setup because we already have the key, we already know what cipher we're going to use, so we can streamline things quite a bit. And if you use HTTP 2 with TLS 1.3, you can get it down to just 2 round trips. It still has to establish the TCP connection, but the TLS and HTTP layers end up combined. But with QUIC, we can go one better and actually combine all 3 layers into a single round trip, which means effectively there is 0 overhead to using encryption in this situation. But there's a problem with resuming these sessions. Part of the data that we've thrown away or skipped by using this resumption, it means that there's a potential for replay attacks. If an attacker captures some of the traffic between client and server and then just plays it back repeatedly at the server might have a hard time telling that it's actually not legitimate request coming from the client and it's actually an attack. And for that reason, this tends to actually be disabled by default. The other thing is that you can't rely on the client telling you that it's done this, because it might be lying. There may have never been a previous setup. And so you can get, on the receiving end, which would typically be, say, an Nginx proxy in front of PHP, it'll receive a request that is this kind of shape, and it will add an extra header called early data. And this will be set by your inbound HTTP interface. And if your application chooses to reject that, it could return what's my new favorite HTTP error code, which is 425, too early. It's the kind of thing you want first thing in the morning. But also at the moment, this has only been implemented in Firefox. So anyway, going back to head-of-line blocking, this is what happens with HTTP 2. So here we have 3 resources being transferred over a multiplex TCP connection in HTTP 2. Over here, we have 1 resource in red, and then we've got a second resource in green, which is number 4, 5, and 6. And this 7 and 8 here is a third resource, which we're using the prioritization features of HTTP 2 to allow us to sneak this data past. So if we imagine that this green one is, say, a big image, and the blue one here is a critical piece of JSON data that was transmitted after that image, but we'd actually like to give it a higher priority because it's more important that that data gets there than the image, we can actually prioritize it higher and actually sneak it past in the pipeline. But then there's a problem. TCP has no idea about HTTP or resources. All it sees is a stream of packets that need to arrive in the right order. So if this number 1 packet here is held up for some reason, it's been corrupted in transit, and we need to ask the server to retransmit it, everything else in the queue is going to be held up. And this is head-of-line blocking. So the thing at the front can cause problems for everything else. So in HTTP 3, we solved that problem by having multiple streams within our single connection. And this is done quite differently to how it works in HTTP 2. They're not just all in a line. UDP doesn't care about whether packets are in the right order. You just send them. However, because we still do ultimately want our resources to turn up intact, we can treat each of them completely separately, effectively exposing the fact that these things are separate resources right down in this low-level networking layer. So say there is a problem with this number 1 packet here. Sure, it's going to hold up the rest of the parts of that particular resource, but the other ones down here can just carry on. They're not going to be held up. So we've solved the head-of-line blocking thing. And just to give you an idea of how much can go in here, Nginx defaults to allowing 128 simultaneous streams. Network switching. When we're using TCP, the way that a client is identified to a server is by the combination of its IP address and the destination port number. Not the source port number, sorry, not the source port number, not the destination port number. The destination will always be 443, but the source port number might be something different. Now, when you do something like switch from your local Wi-Fi to a mobile connection, you're going to get a new IP address, and you're probably going to get a new port number as well. And that means that as far as the server is concerned, you're a completely different person, unless you're unifying those things through some other mechanism at a higher level by things like cookies. But down at the networking layer, you effectively look like a completely different person. And this means that it breaks session resumption. So we're going to have to reestablish all of these connections again. So QUIC uses a completely different approach. The first time you connect, it will give you a connection identifier. And every time you switch networks, you can reuse that identifier. And it then knows that you are the same person across multiple networks, and it can still use session resumption. But you might think, well, with TCP, every time you switch networks, our privacy is protected because it doesn't know we're the same person. But QUIC thought of that as well in the design. And instead of you just being assigned a single ID, you're actually given a list of them. And every time you switch networks, you just use another value from the list. And these connection IDs are actually just random numbers. So they contain no data of themselves. They're pure identifiers. We saw HTTP 2 added compression, but it does this in a certain way. It's basically like a zip file, that if you have a collection of packets, it compresses all of them, and when they're received, it can then decompress all of them. But the problem is that if those packets don't arrive in the right order, it'll have to wait around until it's received them all, and then it can decompress them. And this can actually cause another kind of instance of head-of-line blocking, that we're sitting there waiting for bits of it before we can start decompressing. HTTP 3 uses a slightly different thing, which compresses each packet individually, and that means that we get slightly worse compression ratios, but we don't run into the head of line blocking thing. As soon as we receive a packet, we can immediately decompress it. So obviously we need to actually implement this stuff. We've said this is all happening in userland. So first of all, there are 3 places it's going to get implemented: clients, servers, and libraries that support both. So on the client side, not surprisingly, the first one to support it was Chrome, because after all, it's a Google invention. And then everything that inherited from Chrome, like Edge. And then it was also implemented in Firefox and Safari, though Apple have been doing one of their typical things of doing a kind of progressive rollout. So you may or may not get this actually working, and we can see that possibly happening in a bit. On the server side, Lightspeed was the first implementation. Caddy, it makes it super simple. It just works out the box without having to do anything at all. Nginx supports it very well, and it's also supported by HA proxy. But most significantly, it's not supported in Apache. So now might be a good time to switch to something else. If you're implementing an application where you're using HTTP directly, libcurl and OpenSSL support HTTP 3, but there are also some newer libraries that are slightly more focused on specifically HTTP 2 and 3. I mentioned earlier, Cloudflare is an early adopter, and other cloud providers as well have also started using HTTP 3. So you may not have to do anything to get HTTP 3 visible on the outside of your system, but on the inside you still use whatever you like. But to the outside world, it looks like you're using HTTP 3, so you can gain some of the advantages there. But again, this is all in userland, so anytime that we want to add a new feature, we're free to do so. We don't have to wait for an operating system update. So how are we going to deploy all this? Well, there's one basic problem here. How does the client know that it can use HTTP 3? Because if we just try to use it and the server doesn't support it, we're just going to be waiting forever. And we don't really want to use a timeout because we've already annoyed our users enough by that point. So the server needs a way to tell the clients what protocols it can use. And there are 2 mechanisms available for this. The first of these is an HTTP header called alt service and a DNS record type. Let's have a look at both of these. There's an RFC for that, and this is short for alternative service. And it uses a similar kind of approach to strict transport security for HTTPS. And this is what a record looks like. So we have our alt service is the name of the record. H3 is the code for HTTP 3, and it says that that's available on port 443. And this is implicitly UDP, not TCP. It has a max age value of this number, which is 1 day in seconds. You probably know and love this number. And we've also got an additional thing here, which is persist equals 1, which says that it should remember that even between browser restarts. Otherwise, it will just reset the number. So once a browser, and then down here it says that it's also available as HTTP 2, also on port 443, and for the same duration. So having seen that, the browser can then remember that this host name is accessible over these protocols for this amount of time. And it will continue to do that. And I can show you a very nice little interaction that demonstrates exactly this mechanism working. On the DNS side, we have these service binding records. And in particular, it introduces this new HTTPS record type. This saves you an HTTP request to find out whether HTTP 3 is actually available, but at the cost of a DNS lookup. But the DNS lookup looks like this. So here we've got the example.com domain, a TTL of 1 hour, the HTTPS record type, the priority 1 for the root of the domain, and Alpen, which is part of the TLS nomenclature, says that it's available over HTTP 3 and 2 in that order of preference. Now, when we visit a website, of course, one of the things that we're going to have to do is a DNS lookup anyway, because we need to find the IP address from the name. So wouldn't it be cool if we didn't have to do another request? Fortunately, we can actually get both things at once. So you can actually add in these hints for IP4 and 6 to add new IP addresses into that response. So we can do a single DNS lookup and find out the IP address to connect to and find out what connection protocol that we can use. The priority value here means that we can have multiple records that give alternatives to where we actually go to do this. So this is saying that example.com is also available as example.net and also available with HTTP 3 and 2. And it's also available as example.org, but only over HTTP 2. And this value here, 2, is larger. And just like MX records in DNS, the lower the number, the higher the priority. So next thing to go on to is how do we configure Nginx? If you've configured, well, this, I mean, you have to do something similar in other browsers apart from Caddy, where it's just all invisible and automatic. This is how you configure stuff typically. So we've got 2 listen directives for our secure service, port 443 SSL. That's what they call, that's just the old name for TLS. But then we've got these 2 new ones that we say that we're supporting QUIC. And this also implies that this is going to be UDP and not TCP. And then we turn HTTP 2 and 3 protocols on. And here we're telling it to deliver the alt service header as well, so that we can tell the browser that those services are actually available. Of course, we can't just do that. We also need to make sure that it's actually accessible through the firewall. So we need to do, this is using UFW, the uncomplicated firewall, which is the default firewall system for Debian and Ubuntu. If you just say, allow any traffic to port 443, by default, it'll actually allow traffic on both UDP and TCP. But you can be specific by specifying proto-UDP as well. If you're using raw IP tables, you specify that it's UDP protocol on port 443 and that you accept it. So QUIC requires TLS, and it requires TLS 1.3 specifically. Well, TLS has actually been around for quite a while. My first conference talk on it was actually back in 2016. But QUIC makes it a requirement. And TLS 1.3 brought us some really useful features. It has much lower overhead. We saw earlier that it can save you round trips on the TLS handshake. It has no weak cipher suites, key exchanges, or hash functions. So essentially, it's impossible to configure it in a way that's not secure. It has forward secrecy in all of its cipher suites. And that means that if somebody captures the traffic between the client and server, even though they can't read it because it's encrypted, if they later on manage to get hold of your private key, they still won't be able to decrypt it. It also has downgrade detection, that if the client and the server both support TLS 1.3 and some man-in-the-middle attacker tries to downgrade it to a less secure protocol, you can spot that happening and reject the connection. I mentioned before that QUIC is kind of like a big TLS extension. And because of that, more of the data that is transferred is encrypted, because more of it is effectively on the inside of the encrypted transport. Whereas in TCP, for example, the headers of the packets themselves are not encrypted, whereas in QUIC they are, because they're kind of on the inside of the TLS layer. Something I was asked about the last time I did this talk, about 3 weeks ago, WebSockets. So yes, HTTP 3 supports WebSockets. There's an RFC to do it. And in this RFC, which is, I swear, it's one of the shortest RFCs I've ever seen. I think it's got like 2 paragraphs. And all it does is just defines a single new value that allows you to say that it's going to be able to use HTTP 3 and not just HTTP 2. But much more interestingly, there's a new thing called Web Transport. And Web Transport supports multiple streams over a single connection. It has unidirectional streams. They're not always two-way in either direction. You don't necessarily have to guarantee that delivery occurs in any specific order. And you've got a choice between reliable and unreliable transports. Now, this should all ring some bells, because this is, of course, exactly the features that we get from using UDP. And rather than just implement everything that TCP does and force everything through a TCP-like layer, we've still got access to some of the features that UDP provides. So say, for example, you're doing a WebSocket that's doing things like transmitting your mouse position, or accelerometer data, or geo-IP data. It probably doesn't matter if you drop the occasional packet of those. It's not really that important. It's the continuation of the stream that's a higher priority. And so that kind of thing, where we don't necessarily want a WebSocket being hung up because it's waiting for retransmission, we can go, just don't worry about it. Use an unreliable transport instead. That's an option that's actually not available at all if we're using TCP. We just don't get the choice. It's all or nothing. Either your data gets there fully intact or it doesn't get there at all. So how do we go about optimizing our sites and apps for HTTP 3? Well, this is pretty much the same as for HTTP 2, really. The key things are to only use a few domains, because every time you have a new host name, you've got to do a new DNS lookup, you've got to do a new TLS handshake. There's quite a bit of overhead to doing that. So keep that number down. Don't really need to worry all that much about bundling. The request count isn't really that important. Now, I know people get very hung up on using things like Webpack and Vite to bundle everything together in single things, but there's a lot of effort involved in doing that. And those bundled resources can get really big, and every time you change them, they get completely rebuilt, and they're kind of expensive. And also, because it's just a single HTTP request that does that, it means that the browser has no opportunity to try and optimize exactly the mix of things that it requires to render any particular page. Now, this is something that 37 Signals have actually really jumped on recently, that they've actually switched, and they don't use any bundling at all. They deliver all of their JavaScripts individually through individual requests. And although that represents a lot of overhead on the request side, the requests are tiny compared with the amount of data coming back with the response. So your actual bandwidth consumption is really not changed all that much. But it means that the browsers get to optimize absolutely everything, and it means that only the exact resources that are needed for a page are used each time, and it's decided automatically by the browser. It's not something that you have to worry that much about. But that doesn't mean that you shouldn't take advantage of the features that we do have, so use defer, preload, async, and lazy loading. Now, there's another little thing, which is not really new. This standard actually appeared in 2017, but it was only really implemented in HTTP 2. However, it's much more effective in HTTP 3 due to the improvements in the multiplexing. So this is a regular response. We're using early hints. So this says it's a regular HTTP 200 OK. It's a 1.1 because it's from 2017. We've got a content length. That means that we know exactly what we're delivering at this point. So this is after we've finished all of our back-end processing. But we give it some additional headers here. That means that we can give hints to the browser that it's like, hey, we're going to need these resources to render the page that I'm about to deliver to you. So you can go and request them now rather than waiting until you've passed the HTML to find out the same information. So these early hints allow the browser to get ahead of things a little bit. But there's an alternative way of doing this using these early hints. And this is actually a single response. It might not look like one, but it is. Because up here, we've got a 103 early hints response type, and we've got these same link headers we saw here. But notice that we've got no other data. We've got no information about the content type or the length of it. We just say, you're going to need these resources in what comes next. Or more to the point, you might need these resources in what comes next. It's actually possible to have multiple sets of these. So you could have a whole set of them stacked up. And then you get a break between them, and then we get our regular response following it. So these can occur multiple times while the backend's thinking about what it's actually going to render and deliver. And your browser can go ahead and do things like either preload, or the other option is pre-connect, which allows it to go and do DNS lookups before it needs them. But then when it actually comes down to it, it's these ones down here that are actually going to be implemented. So it's entirely possible that you might have said this up here, and it might not actually be true by this point. You might have changed your mind. So these are hints. They're not hard and fast rules. So that they can be wrong. But it's just interesting to see that effectively you get multiple sets of headers in a single response. So having done all this setup and things, we want to make sure that it actually works. And so we need the ability to test things. So when I was writing my book, I ran into exactly this problem, that I needed to be able to show the differences between how things are delivered. So I wrote this little setup here, which is actually 3 different host names that allow us to pick the protocol as we go along. I'll show you that in a moment. Then there's http3check.net. You can just go there, put in your host name, and it will it'll tell you whether you've configured it right. There's an HTTP indicator Chrome extension that puts a little lightning bolt that changes color according to which protocol you're using. And in the developer tools, there's a protocol column, though it's not enabled by default. And if you right-click on the table header in the network tab, you'll find you get this protocol column, which tells you the version number of the protocol it's using. But remember that because the browser doesn't know whether it can use HTTP 3 or not, it will request it over HTTP2 first. And this makes testing a little bit tricky. So let's have a little demo of that. Oop. So this is the HTTP3 check thing. You see I've pointed it at my own thing here, and it says that yes, indeed, this does support HTTP3 and it does support QUIC, and it gives you some other stats about it. There's more stuff lower down as well. Tells you all the headers and so on. So this is the site that it's testing. So this is very bare bones, no tailwind in here. It renders the same page over different transports. So what I'm going to do is make it so we can see this. If I reload that, you can see that in this protocol column, everything is being loaded over HTTP 1.1. And then if I just go over here and load it over HTTP 2, we get a slightly different background color, and now everything's being delivered over HTTP 2. But at this point, it still hasn't seen a header that says that HTTP 3 is available. I deliberately made that. So I hit HTTP 3, and it still delivered it over HTTP 2. Because at the point it sees the header, it's already too late. We're receiving the data by that point. So we can't suddenly switch in the middle of a single response. And the browser's going to take a little while to figure out that it can do that. And so what you'll often find is you get these H2s down here, but then look what happens here. Suddenly, it's managed to pass this enough to figure out that down here, it can switch to HTTP 3. So now that it's seen that, the other thing I can do here is, if I click that, we can see that we've got an out service header here. Well, I've only configured HTTP 3. You don't necessarily need to have the HTTP 2 one because it's kind of assumed. It's there by default. You can specify it if you want to specify, for example, that it's available on a different port. But you notice I've given it a max age of only 10 seconds. And that means that if I request this again, it's going to be over HTTP 2 again, because it's forgotten at this point. But I do it now, we're on HTTP 3 for everything. And if I just stand here and talk for 10 seconds and twiddle my thumbs for a bit and wait until it's done it again, and I load it again, it's gone back to HTTP 2, so it's timed out. And I hit it again, we're back to 3. Now, if you roll over this column here, it will tell you something here. This will tell you why it chose this protocol. So here it's saying that it simply did what it was told by the header. But sometimes you find that it will give you an alternative thing because the browsers optimize really heavily, and they might issue the same request over both protocols and see which one's faster. And whichever one wins, it will then use for subsequent requests. And this makes testing a little bit tricky because we're never quite sure which protocol we're going to get. I need to be back in here. Right. So overall, is it actually faster? Well, as we've seen, it depends somewhat because it's actually slightly difficult to measure. But fundamentally, it works best where its features are going to make the most difference. So if you benchmark it from fast domestic broadband or your company connection, you're unlikely to notice or even measure a difference between them. But if you're up a mountain, the other side of the world, with a weak signal, switching between roaming services during a major sporting event, it's much more likely to help. Google reported about a 14% speed improvement for the slowest 10% of users. The thing is, if you're optimizing stuff, you don't really care that much about the people that are having the best time on your site. It's the people that are having a bad time that you need to concentrate on, and that's exactly what HTTP 3 and QUIC help with. You know, if your website takes 20 milliseconds instead of 22 milliseconds, no one's going to notice any difference. But if it takes 50 milliseconds instead of 300 milliseconds, you will notice a difference. Fastly and Wix also reported an 18 to 33% improvement in time to first byte. So it's just like those little increments that just improve things across the board for everybody. There are occasional problems. Networks might